Dimensional tolerances are a crucial part of the design and manufacturing process. A tolerance is a numerical range of measurements assigned to a part's dimensions, indicating how much a manufacturing team can drift from the nominal measurement. Tolerancing helps ensure that manufacturing parts meet design requirements while accommodating variations in the manufacturing process, material properties, and assembly procedures. It is essential for achieving the desired functionality and interchangeability of components in various engineering applications. In this video, I will demonstrate how to understand and apply tolerances, as well as employ construction geometry to create a part. Welcome back to Practical AutoCAD and Inventor, your source for practical solutions to your problems with AutoCAD and Autodesk Inventor. If you like these videos, please like and subscribe so you will be notified whenever new videos are published. Also, if you have any questions you would like me to answer, please leave a comment below. Now, on with the video. Dimensional tolerancing is a system used in engineering and manufacturing to specify and control the allowable variations in the dimensions of a part or assembly. It ensures that parts fit together properly and function as intended while accounting for inevitable variations in manufacturing processes. In dimensional tolerancing, each dimension on a technical drawing is accompanied by a tolerance, which defines the acceptable range of variation from the nominal dimension. Autodesk Inventor has several methods for tolerancing, with the most common being symmetric, deviation, and stacked limits. Each method has unique applications. For example, let's consider a simple mechanical part, a shaft with a diameter of 25 millimeters. The drawing might specify a dimensional tolerance as follows: 25 millimeters plus or minus 1.1 millimeter. This means that the acceptable range of diameters for the shaft is from 24.9 millimeters to 25.1 millimeters. Any shaft diameter within this range is considered acceptable and will function correctly within the assembly. Next, let's take a look at the example on the screen. In this example, there are several dimensions that are regular nominal dimensions that do not express any tolerance. These would be things like 1 15/16, 2 1/4, 7/8, or 9/16 radius. On the other hand, there are several dimensions that have tolerances. And in this case, they're all stacked limits dimensions. So for example, the overall thickness of this part that sticks up, it can be as large as 0.625 and as small as 0.623. The hole that goes through this part can be as large as 0.502 and as small as 0.500. There's a note here. This is actually incorrect. The bigger number should always go on the top and the smaller number should always go on the bottom. Same thing down here. Your hole, the largest tolerance, the upper limit should be on the top and the lower limit should be on the bottom. So you can see that this part uses tolerances in several locations. Here, the size of the hole, the size of this hole, the overall width of the part, the clearance in between the forks, and the clearance of the slot there. There are also a few dimensions on this part which don't really need to be there, that don't make sense. For example, this 1/4 inch dimension right here does not really need to be there if we assume that this part is symmetrical. We know the overall depth is going to be between these two numbers, and the depth of this part right here will be between those two numbers. We can assume that the outer edges will be the same. It's not quite 1/4 of an inch, but it's close. Same thing with this 5/16 of an inch here. The nominal distance of that is going to be approximately 5/16, but it's not exactly 5/16. We're given better information on how big they should be down here using these tolerances. When it comes to dimensioning, when you have a dimension that has a greater level of accuracy, you should always use these numbers and not these numbers that have a lower level of accuracy. One other thing that we will do when we create this part is we will use some construction geometry so that we can get things aligned. In order to figure out, for example, this 15-degree angle, we're going to employ some construction geometry so that we can keep these parts in the correct orientation. One final design factor to consider is that in this part, the x-axis here is going to line up the center of this circle and the center of this slot. But the bottom of this part is not parallel to that x-axis. You'll notice that the radius of this arc is 13/16, but from the center of the slot down to the bottom is only 11/16. So these two lines are not perpendicular, and furthermore, this angle right here is not 90 degrees. So we're going to begin by creating a new sketch. We're going to place our x and y axes in the drawing as construction geometry. We'll add this construction geometry, and then we'll start our part. So looking here in Inventor, I'm going to say I want to start a new sketch. I'm going to pick that front plane and to begin my sketch. Now as we look back at the part, because of the nature of this part, I will be able to embed all of the information that I need for this part into one sketch. I will not need to do more than one sketch. I can put everything I need into this one sketch. Then I can share this one sketch several times and create several different extrusions. So the first thing I want to do is I want to project my y and x and y axes as construction geometry. Construction geometry is special because it is not considered by the program when we're creating extrusions or revolutions. It's there just for construction purposes, and it'll be ignored for the purposes of profile geometry. So I'm going to go up here and I'll use this button right here to turn on construction geometry. And then I want to go to project geometry and make sure that I have my origin expanded, and I'm going to click on my x-axis and my y-axis. And you can see now that those are projected into the drawing as construction geometry. They look like dashed lines. Again, they're going to be ignored for the purposes of profile geometry. The other thing that I want to do is I want to draw a line that will represent this distance from the center of this circle to the center of this circle. So it'll be about 2 inches long at an angle of 90 or 15 degrees from vertical. So I'll start right here at the center, and I will make it approximately 2 inches long at an angle of, about 15 degrees from vertical. It doesn't have to be exact. We will dimension it later. So now I'll turn off my construction geometry by just simply clicking on that button again, and I can start my part. So on the left side, we have that arc that has a radius of about 13/16. That corresponds with a circle with a diameter of about 1 5/8. So I'll make my circle approximately the right size and shape, and then I'm going to put my line in. And remember, when we connect this line, ultimately we want it to be tangent right about here where I'm connecting, but make sure that you don't get it right at the quadrant. Notice that it wants to jump to that quadrant, and if I connect it to that quadrant, I'll never be able to get it tangent up here without deleting that constraint. So I'm purposely going to pick a point that's not at that bottom quadrant. It's going to come up about like this, about 2 1/4 inches. And then I've got my slot that I need to create. And again, this needs to be a vertical line, not perpendicular to that previous line. So I'll make sure that that's vertical. And then I'm going to put my slot in. Get it approximately the way I want it, and then I will stop here for a moment. Now looking at this, if I show my constraints, you'll see that I've got my tangent constraints between the arc and the line here, my tangent constraints between the arc and the line here, but there's no tangent constraint here. So I'll go ahead and apply that one so that it's here. The other thing that I want, if we look at the previous drawing again, is the x-axis needs to go through this center right here and also along the center of this. So I can apply a coincident constraint between this center point right here and my construction geometry there to make sure that I maintain that. One more that I'll put in is I want this line right here to be equal in length with this line here. So now from here, you can see that we're pretty stable. We've got a good solution. We've got the bottom portion of this all the way through here. Next, I'm going to draw the line that comes up and around the top and then back over to here. So we'll use the same method. I'll start with a line. It needs to connect about here. It's going to come up about like this, and don't worry that it's not tangent just yet. I'll make my arc come over. Okay, again, I'm not too worried that my points aren't all joined exactly where they're supposed to be. And then I need one more arc that will come back down here to that point. Okay. From here now I will come in and I'll put in a few constraints. I want that to be constrained to there with a tangent constraint. Okay. And I need this point to be on the end point of that line. So I'll put a coincident constraint between those 2 points. Now I don't really need the rest of this arc, so I'll use my trim command and I'll get rid of the parts of that arc that I don't need. And notice that when I do, I still have all of my constraints. Sometimes you will lose one of these tangent constraints, so you always want to make sure that you still have those tangent constraints in place. But now that they're all in place, I can actually begin to place my dimensions at this point. So looking at our part here, our overall length, well, the length from the center of the circle to the end is 2 1/4, and then the length of that line is 1 15/16. So I'll put those two in first. I like to begin with my largest dimensions and then work to the smaller dimensions. So from the center of that circle to that point right there, it's 2 1/4. And then the length of this line is 1 15/16. Notice that it wants to give me a vertical dimension, but if I click on that line one more time, it gives me the ability to do an aligned dimension. So that one needs to have a dimension of 1 15/16, 1.9375. Before I go any further, I'm going to put that 15-degree angle dimension in there. So the angle between that line and that line needs to be 15 degrees. That'll help hold things in place. Now I can come in and continue to put other dimensions in. This one has a radius of 13/16, which is 0.8125. This one has a radius of 9/16, 0.5625. This one has a radius of 2 5/8, 2.625. And then over here, we've got some of our tolerances. Okay. First of all, we have 1 3/8. That's not a tolerance dimension. But we do have a tolerance on this slot. Okay, so we're going to figure that one out here in just a moment. And we have 7/8. So I'll come in here and I'll say the dimension from that point to that point is 1 3/8. And then the dimension from there to the center of that circle is 7/8. And now all I have left to do is to dimension the width of this slot. And this will be our first dimension. So to do so, you just start with your regular dimension command. From there to there, and I'm ready to put it down, drop. It says that it's going to be 0.64 or whatever. But my actual dimension that I want has an upper limit of 502 and a lower limit of 500. So I'm going to change that to 0.500, and then instead of hitting enter, I'm going to hit this little arrow right here next to the dimension, and notice that there's an option here for tolerance. There are several different tolerance options. Basic is just the nominal value, whatever you tell it that you want it to be. So we're not going to be using basic. Symmetric is where the deviation above that value is the same as the deviation below that value. So it would be like 0.500 plus or minus 0.003 inches, which would make the upper limit 0.503 and the lower limit 0.497. Deviation gives you the option of having a different upper limit and lower limit. So it would be 0.500 plus 0.003, but minus 0.001, so that you could have different deviations from that nominal value. But this one calls for limits stacked. So we're going to use the stacked limits. And what it does is it just allows you to say the upper limit of that is this, and the lower limit of that is of this dimension is that one. I had already changed it to 500. That's why it filled both of these in. And I'm just going to say that the upper limit is 0.502 and choose OK. Now it'll still say 500 here, but when you hit the green check mark and you say OK, notice that it adds your stacked dimension in there, which matches what we had in our part, 502 over 500. From this point now, I can simply put in the rest of these. I need a line here that's going to be the back of that slot, 1.5, and I've got some geometry up here. So I've got a 3/4 inch radius and a 3/8. I'll add this stuff in first. Looking at this, I'll come in, I'll say I want a circle, and it's got a radius of about 3/4, and then there's a line that goes horizontal like this. I can trim off what I don't want, and now I can dimension it. So this one has a radius of 3/4, and my distance between that and the center of that circle is 3/8. Okay. Again, we're still fully constrained. I need to add one more line. So my line is going to go from about there to there. It needs to be vertical. And the distance on this will be from there to there is 1.5. So now I have all of my geometry that I need to finish this part and to do the extrusion. So I'll say finish my sketch, and now I can start with my extrusions. If I look at the part here, the middle part is the thickest. So notice the fork here, this is the thickest, and it has a tolerance. The maximum extrusion is 1.152, and the minimum distance there is 1.150. So I'm going to extrude that portion first. I'll come in here and I'll say I want an extrusion on this. It's going to be this and this. Because of the nature of this part, I'm going to do a symmetrical or mid-plane extrusion. I want that distance to be 1.150, but I want a tolerance. So again, I'll go to the little button here that has the arrow on it. I'll choose tolerance, and I'll say, okay, again, I want that stacked limits, and I want to change that upper limit here to 1.152. Say OK, and now we can say OK, and that first portion is done. Now I put a lot of information in that sketch that I'm going to reuse. In order to reuse it, you expand your extrusion, right click on sketch 1, and then we'll choose right click on sketch 1, and we'll choose share sketch. Now that the sketch is visible again, I can use this same geometry to create more geometry. So again, I'll say extrude. This time I'm going to pick that part, but if we look back at our sketch or our drawing, it's got a stack tolerance of 625 over 623. Okay, so I'm going to say, okay, I want my distance to be 0.623. I go to my tolerance, and I want the upper limit to be 0.625. Oops. 0.625. My lower limit is 0.623. Say OK, and then OK, and that portion's done. And now we need to cut out the middle portion, okay, to make the forks. So again, I will use my extrude. I can pick that portion, and then on this one, the numbers are again different. It's 0.531 over 0.521, okay? So I'm going to say it's going to be a cut feature, and my distance here is 0.521. If I look at my extrusion here, tolerance, okay, now I can say I want it to be 0.531 over 0.521, choose OK, and then OK, and we're done with all of our extrusions. I'm done with all of the extrusions. I'm happy with what they look like. So now I can come back in, right-click on Sketch 1, turn the visibility of that sketch off so that it's not in our way anymore. The last two things that we want to do is add our holes. There's going to be a ream down here with a diameter of 750 and a hole up here with a diameter of 0.5. Starting with this one, we'll use our placed feature. The advantage of a placed feature is you don't have to create the sketch, it will create the sketch for you. And we want this hole to be symmetric with that, concentric with that corner. So I'll say I want a hole through this on that surface. It's going to be concentric with that corner right there. Okay. My diameter, if we look back at our sketch, has 750 over 751. All right. So I'm going to give it my diameter here, 0.750. But again, I want a tolerance, and I want that stack tolerance, and my upper limit is going to be 0.751. Say OK, and OK. I need another one up here the same way. So again, hole on that surface with that concentric reference. On this time, the diameter is 500 or 502 over 500. Okay, so I'll come in here and I'll say my value is 0.500. Again, I want it to be a stack tolerance, so I'm going to say my upper limit is going to be 502. Say OK, and then OK. So now that part is completely modeled. You're ready to save it. Now that I've saved it, I can create the drawing. I'm not going to do the whole drawing, but I will show you that the tolerances have been preserved. So if I come to the drawing here, I can say I want my base view, and my top view, and my side view, and even an isometric view if I want it. And now when I'm ready to put my tolerances or put my dimensions in here, right-click on the part, choose Retrieve Model Annotations, and you'll see that they're all here. Notice that my 502 over 500, that's that stack tolerance that we put in there. It's there, okay? So I can say I want that one, and I want this one. And you can pick the ones that you want, then you can arrange them wherever they need to be. Okay, obviously there are going to be problems with this, but it does include those so that you don't have to worry about going back in and putting them in later. It also does for the holes and for your extrusions as well. So if I come to this view, or maybe the top view, I right click on this view and say retrieve the model annotations. Notice that I've got my tolerances here as well. Okay, so they're all there.